Hello again, and welcome to the next episode of my Machine Learning the Basics series. In this episode, we're going to take some of those basics that we learned in the last episode, and we're going to actually apply them to something. In this case, we're going to be doing a linear regression. It's going to be a simple linear regression. So we're going to basically have two variables. And in this case, I have some data already that I've pulled from Kaggle. I'll make that data available on probably my GitHub, as well as a link to the original Kaggle post. And this data is just some population data for the United States over, I think, 50 or so years. What we're going to do is we are going to write a simple linear regression, and we are going to use no libraries to do it. That means that all of our code and everything will have to be written specifically for this case. And the reason I'm doing this, I want to kind of break down the numbers in and of themselves without any kind of fluff. And then as we start going into more complex topics, we'll obviously be using more and more libraries at that point. But to start this off, I figured using no libraries would kind of show you a little bit of what you're, what magic you're getting when you're using some of these well-known or already established libraries. So what exactly is a simple linear regression? A simple linear regression is, in a way you can think of it, if you've ever seen one of those charts where you have an X and Y dimension and there's a bunch of points on it, what a simple linear regression will do is it will plot a straight line through the center of that cloud of points. This is useful for prediction. If you see a lot of things going in a very specific way and they're clustered in these specific ways, we can use a simple linear regression to find out whether we have a positive or a negative regression and plot. So what we're going to be doing in this specific lesson is we're going to build out one, and we're going to run it against the population data, and we will in essence be using the year as well as the population count to make a prediction on what we think the population should be during any given year. And then we'll all put that together. Now, I did say we weren't going to be using libraries, but there is one library that we will be using, and that is Pandas. And Pandas is a kind of a very helpful library for us because what it allows us to do is to package our data into a very accessible format. So we will be using that just to make the data more accessible as well as making it easier to understand. And then as we start exploring the data, I'll explain kind of the process as we go. Sweet. So now that we've kind of gone over those basics and whatnot, let's actually start with some code. As I said before, we're going to need to import Pandas. Make sure that you have it installed. If you don't have it installed, simply typing pip install pandas wherever your Python install is set up. We'll set it up, and I already have it, so there's no need for me to download it. The next thing we're going to need is we will need the POW from math. So from math, we're going to import POW. So you'll also need the CSV file. Like I said, I'll make that available. Link to it should be in the description of the video. But it is just population.csv, and that is currently in my current directory that I'm in, so I do not have to worry too much about anything like that. Corpus. So the corpus is our entire data set, and we are going to use Pandas to read the CSV. This is another reason why we're using Pandas, is because it makes things like accessing a CSV or a JSON, file, we can just kind of crunch this down. We don't have to worry about parsing anything. We just load it into a data frame, and Pandas handles all the nitty-gritties. Luckily, all we're really going to use it for is building this data frame so that we can access things really easily. So one of the things we're going to do is we're going to run our corpus. Now, this doesn't do anything because we haven't defined what run is. So this is going to be like our main function here. If you're working on Python 2, you can use the __main___ system variable to actually define like, hey, this is where the program enters. In this case, because we're just doing really simple Python 3 stuff, I'm just going to call a function to start this program. So right now this doesn't do anything, but we'll just leave this blank as we go. So one of the things we need is our mean. So let's go ahead and just do that. That's a simple one. So we're going to say our total is sum of list, and our size, is the length of list. Ooh. If I could figure out how to type, right? And then our mean is simply total divided by size. Well, let's go ahead. That is the wrong button. Let's go ahead and add some space in there, and we will return this value. So let's just return that. Okay. Now list, we're going to pass this in. This will be whatever the list item that we're going to be. So we're going to be basically everywhere through this program, we're going to be passing a list of numbers just everywhere. So let's get used to it. So let's go ahead and implement our difference. So this is going to be used in our covariance calculation. And difference is simply going to be a list, and then we're going to get our list's mean. And that's going to be mean list. And then what we're going to do is we're going to return, and we're going to do a map, and we will be doing an item minus the list mean. Let's go ahead and add some spaces in there. Getting lazy on the spaces today. For item and list. Boom. Looks right. Let me double check. Looks right. Okay. Get rid of those spaces. That is our difference. One of the next things we'll need is our difference squared. Difference squared. Now the reason we need difference squared is this will be used in our standard variance, and we do need to square. That's why we brought pow in. So this one's actually very similar to the other one. So what I'm going to do is I'm going to copy this, paste this in here. And when we look at this, the main difference is we are going to pow this to the power of 2. Oops, that is an @ sign. And let me double check my syntax. This looks good. Okay, for item and list. Okay, so yeah, and so we're mapping through, we're raising to the second power the difference in these two values, the mean and the item. So we're getting the mean, and the actual value. We're finding the difference, and then we're raising that to the power of 2 for every item in this list, and then we're returning that. And that is the difference squared. And we use those to find the variance. And so since I keep talking about variance, let's actually just implement variance. And this is list. So our diff is going to be our difference squared with our list. So we're going to pass our list through. And then our variance is going to be sum diff. So we're adding all of these values together, and we're saving this as variance. This is a little bit, this naming's a little off. I should probably change it because the whole thing returns a variance. Variance length list minus 1, and that's the formula to find the variance is a sum. And so we're actually just going to call this total. There we go. So yeah, so we're actually going through every item, and we're doing our difference squared, saving that as diff, and then we're adding all the values together to find our total. And then we're taking our total and we're dividing it by the size of our list minus 1. And that is our variance. And that is one of the formulas that I did not cover in the first episode of this. Now to the kind of like the meat and potatoes of this, the covariance. Because the covariance is what helps us kind of really figure out our plot for our function. So we're going to need 2 lists for this. We're going to have an X list and our Y list. The reason I'm naming them so kind of like methodically, kind of like clinical instead of having good, like easy readable names is I base this off of the exact formula. So it uses X and Y in it, and I wanted to keep things together. So feel free to name these things a little bit nicer when you're doing this to a specific purpose, for example. You can do that. But 9 out of 10, you're not actually going to implement a lot of these formulas when you're writing production code, because there's no need to do that. This is a learning experience. It's an exercise. X list. Okay, so we got our X list and our X diff. Let's go ahead and get our Y. So we are getting our difference. You'll notice that we're not getting the difference squared because we actually don't want to square these, because we need to have the raw values so we can multiply them across. So we're going to create a cross product, and we're going to map, and we're going to say diff Y. Let's actually write the 4 first. Index item in enumerate, and we want this to be diff X. Okay, so what are we doing? This here is an inline for loop. We're basically saying we want to get the index number and the value of diff X. The enumerate is a function that takes a list and then actually gives you back the index. Otherwise, this would just be the value, and there's no second value. So enumerate gives us the index and the item value, which is why we're using it. So then we have our diff Y, we have our index, and we are going to multiply that with an item. So let me just double check that this looks right. Diff Y index times the item for index item in enumerate. Yep, everything looks good. So this gives us kind of the leeway that we need to calculate this covariance. Like if we were to actually use some of these libraries that are designed for this, we wouldn't have to write any of these. We could pretty much just say, pandas.cov, and that literally will calculate covariance for us given 2 different data sets. But we're doing this manually because we want to learn. So we're going to say year mean equals mean corpus. Now this is our corpus. Now let's go ahead and take a look at our data real quick. So this is our corpus file. It is a CSV file. If we scroll to the top, we'll have real-time start, value, data, and real-time end. So I believe the real-time is when this data was collected or when it was last updated. Don't hold me to that. But I do know that the value is the number of people kind of like in thousands or in 10,000s or something like that. This is like 1.56 million people. And this is the date, which is 1952, January 1st. And so these are the actual values of the population of the United States up to 330 million in 2019. So what we are going to do is we're going to make our estimation and our prediction, and we're going to add that to our data frame so that we can kind of compare the values and see how close we were with our estimations. So let's go ahead and get that field. So we know that the field is date. Let me double check, right? It's date and value. Yes, date and value. Fantastic. All right, next thing we're going to do is we're going to do our population mean, which equals the mean of corpus value. And our date variance is our variance corpus date. Now, we've done all this. Let's get our covariance. Our covariance is going to be covariance. I'm just calling it cove because couldn't think of a better name for it since it's a merger of the two. Corpus date. And we're passing in our second one, which will be corpus value. Okay, so we have this. Now, if you look at the formula for the linear regression, we have to figure out these W0 and W1. So what I'm going to do is I'm going to define W1, which is just a little bit easier. It's just our covariance divided by our date variance. That's it. That's very simple. Our W0 is a little bit more complex, but it's still not very complex. It's our population mean or minus what we found out W1 was and our year mean. So we're gonna multiply our W1 value times our year mean, and then we're gonna subtract our population mean from that. And that is our W1. Now, we are ready to actually predict. Now, predicting in this case is simply following the center point and then seeing how close we are to the actual values. So what I'm going to do is I'm just going to append to the corpus. So now that we've done this, I'm going to append to our corpus our predicted population, if I can learn how to spell. And then the actual formula for the guess is our W0 plus our W1 times corpus date. All right. This looks right. Let's go ahead and give it a once over real quick and make sure everything looks good, and then talk about it in kind of like from a top to bottom perspective. Our guess is going to be done for every single item in the corpus. So basically for each entry here, we are going to add our, prediction here. The prediction is obviously not going to be precise, but what we're looking for is how close our prediction can be. And as a linear regression, that prediction will always be linear. So it's going to go in a straight line no matter how we do it. What we're hoping is that our straight line goes as close to the middle of the distribution as possible. All right, let's take a look here from top to bottom again. We have our year mean. We are getting the mean of every year value. We have our population mean. We're getting the mean of all of our... Oh, I found a little tippy typo. In our population, our date variance, we're getting the variance of the dates. And then our covariance is our date and our value. And we get the covariance of those two values, and they're going to cross product and then return all that. I forgot another step here. We don't just want our cross product. We actually need to return the sum of our cross product. Yes, and it's the length of our list minus 1. So it's just like up here how we sum everything and then we return that total divided by the length minus 1. We're doing that exact same thing here. The only difference between the variance and the covariance is the covariance multiplies these two values together and then gives you that cross product that you can sum together. Good thing I caught that. So let's save this. I love the auto formatting. Lots of excess space here. Hopefully you guys can read it as well. I have been, I enlarged the text size by a significant amount. I was told that it was a little bit difficult to read on a mobile device at 4K. So I just enlarged the font in general. So let's go ahead and look at this. So our mean looks good. Our difference looks good. Our variance looks good. Our covariance. So we have our formula. Let's see if she runs. All right, we see no errors. This is a very good sign. Let's open up our Jupyter Notebooks variables and let's take a look at what's in our data drawer. Okay, this is pretty good. Let's take a look here. We have our predicted population, and we have our actual population. This only looks about 1,000 higher here. That's pretty good. Let's go ahead and scroll down to about halfway. 241 versus 245. This is all pretty good here. You can see ours is trending a little bit high at this point, but as we get down, it's not that high anymore. We're back to only 1,000 difference. So this is looking very linear. Look at this. This one looks really nice. So yeah, it looks like our guess pretty much is working. Our final values here are 330. We have 330, and we have 0. They have 3. So it's within only 300 difference on the final guess. This is really good. We would be able to extend this, our linear regression here, with more years. And we could actually guess the value without having any context. And so we would assume that this curve, whatever this linear regression line is going, we can just extend that kind of infinitely in either direction. And you'll see that for the most part, barring any major differences in population change, we would be able to predict those fairly accurately. So it looks like this was a success. I hoped you learned something, and I hope you join me for the next video as well. But until then, I'll see you around. Peace.